The British Antarctic Survey just dropped the most detailed map ever of what's underneath the ice in Antarctica. And my mind is blown because I had no idea it was like this.
Deep beneath the shifting, brutal desert of the West Antarctic Ice Sheet, something was registering on the instruments that shouldn't have been there. It wasn't a glitch, and it wasn't an echo. For weeks, NASA's low-orbiting satellites had been pinging the frozen continent, sending radar waves deep into the multi-mile tomb of ice, only for the return signals to reveal a massive, highly localized thermal spikes and a dense gravitational pull that defied every existing geological map of the region. What happens when the Earth underneath the ice begins to wake up? Grid coordinate 74 degrees south. The data arriving at NASA's Goddard Space Flight Center did not make sense. When the twin satellites of the Gravity Recovery and Climate Experiment, GRACE, swept over a specific, featureless stretch of the West Antarctic Ice Sheet, their ultra-precise microwave ranging systems registered a localized spike in gravitational pull. It was a subtle fluctuation, the kind of minute variation that usually signals a massive underground mountain range or an unusually dense concentration of iron ore deep within the Earth's crust. But when researchers cross-referenced this gravitational data with airborne radar sounding profiles collected by Project Icebridge, the anomaly transformed from a routine geological feature into a profound scientific mystery. The radar waves, designed to punch through miles of solid ice to map the contours of the bedrock below, did not hit the expected rugged, static topography of an ancient continent. Instead, they bounced off a perfectly defined, circular structural depression, spanning nearly 30 miles across, buried beneath 2 miles of pressurized ice. The sheer scale of the reading sent a shockwave through the nocturnal shift of data analysts. Even more perplexing than the structural footprint was the thermal data. Deep interior Antarctica is a cryogenic vault, a place where the baseline temperature of the bedrock beneath the ice sheet typically hovers just around the pressure melting point, kept stable by the insulating blanket of the ice above. Yet, the thermal sensors on NASA's low-orbiting satellites picked up a distinct radiating column of heat originating from the center of the circular depression. It was a massive thermal plume, elevating the subglacial temperature by several degrees compared to the surrounding bedrock. For a brief period, a tense debate rippled through the specialized team of geophysicists, glaciologists, and planetary scientists tasked with analyzing the feed. They were looking at a concentrated engine of energy buried in absolute darkness, actively altering the structural integrity of the ice sheet from the bottom up. Every pass of the satellite confirmed the impossible. The heat wasn't dissipating, and the gravitational mass was tightly concentrated in a way that defied standard geological distributions for the region. The initial working theories were grounded in the violent history of the solar system. A circular depression of that scale, paired with a concentrated mass anomaly, strongly mirrored the signatures of a major bolide impact, a massive iron-nickel meteorite that crashed into the Earth millions of years ago when Antarctica was still a green, forested continent. If an exceptionally dense asteroid had slammed into the bedrock, its shattered metallic remnant would remain buried deep within the crust, perfectly accounting for the intense, localized gravitational pull registered by the satellite. Over millions of years, the scar of that impact would have been sealed beneath the advancing ice sheet, preserved like a time capsule from an era of planetary bombardment. Geologists on the team began calculating the potential kinetic energy of such an impact, realizing that a metallic mass of that volume would distort the regional magnetic field and create an underground crater capable of trapping immense amounts of residual crustal energy. However, an ancient impact crater alone could not explain the active heat signature radiating through the ice. This forced scientists to confront a second, equally monumental possibility. They were witnessing the birth or reawakening of a mantle plume, a localized upwelling of magma from deep within the Earth's mantle, pushing its way toward the crust directly beneath the ice sheet. While East Antarctica is a stable ancient continental shield, West Antarctica is a geologically younger, rifting zone characterized by microplates and hidden volcanic activity. The discovery of an active mantle plume at these precise coordinates meant that a concentrated column of geothermal energy was actively melting the base of the ice sheet, creating a massive hidden reservoir of high-pressure liquid water beneath the ice. The implications of this were staggering. A subterranean volcano, or volcanic hotspot, under a multi-mile ice sheet acts like a burner under a locked pressure cooker, warping the ice dynamics in ways that standard climate models had completely failed to predict. As the modeling computers crunched the data over consecutive weeks, the true scope of the discovery became clear. This was not a passive feature of the landscape. It was a dynamic, hidden variable that could fundamentally alter the stability of the entire region. The team was looking at a massive subglacial engine, a geological anomaly capable of generating millions of gallons of subglacial meltwater, effectively lubricating the interface between the ice sheet and the rock. The race was on to understand exactly what this hidden feature was, because the massive column of heat radiating from the bedrock was already beginning to reshape the ice miles above it. If the heat source continued to intensify, it threatened to destabilize the terrestrial ice pillars holding back massive glaciers from sliding into the sea. The atmosphere in the lab shifted from academic curiosity to a profound, quiet urgency. They realized that the most dangerous catalyst for future sea level rise might not come from the warming air above, but from a mysterious geothermal furnace locked deep beneath the frozen crust. How do you map a world you can never physically see? How we see through 2 miles of solid water. You can't just roll up with a shovel to solve a mystery buried beneath miles of frozen water. You need a technological toolkit that borders on sorcery. For decades, the interior of Antarctica was a blank space on our planetary map, a vast white void that hid its secrets behind a fortress of impenetrable blue ice. To peer through this frozen veil, NASA and international research teams had to develop an entirely new discipline of geophysical forensic. They had to learn how to use energy waves as their eyes, turning the ice sheet itself from a blinding barrier into a transparent lens. The result is a suite of airborne and orbital technologies that can strip away millions of tons of ice with the click of a mouse, exposing the jagged topography of a lost continent in stunning, high-definition, three-dimensional detail. The undisputed workhorse of this subsurface reconnaissance is airborne radar sounding. Through initiatives like NASA's Project Icebridge, researchers outfitted modified research aircraft, like the rugged P-3 Orion and the long-range DC-8, with sophisticated ice-penetrating radar (IPR) systems. As these planes fly grueling, grid-patterned paths just thousands of feet above the desolate ice plateaus, they blast radio waves straight down into the ice sheet. These aren't your average radio frequencies. They are carefully tuned, low-frequency electromagnetic pulses designed specifically to slice through frozen water. While high-frequency signals scatter and get absorbed by snow and upper ice layers, these low-frequency waves travel through the crystalline ice lattice like light through a pane of glass. When the waves hit a boundary layer, such as the transition point where solid ice meets rock, or where ice gives way to liquid water, they bounce back to the aircraft's receiving antennas. By measuring the exact microsecond variations in how long it takes for these radio echoes to return, onboard computers calculate the precise thickness of the ice sheet down to the meter. But the true magic lies in the data processing. A single flight generates terabytes of raw, chaotic echo returns full of static, interference, and atmospheric noise. Scientists use complex mathematical algorithms to filter out the clutter, transforming the raw acoustic-like signals into crisp visual profiles called radargrams. These radargrams reveal the hidden anatomy of the ice, the internal layers of compacted volcanic ash from ancient eruptions, the warping folds caused by immense tectonic pressure, and finally, the rugged silhouette of the bedrock itself. It was this radar technology that first sketched out the massive circular depression at grid coordinate 74 south, proving that something extraordinary was carved into the continental crust. Yet, radar only tells part of the story. Orbiting hundreds of miles above the planet, the Gravity Recovery and Climate Experiment, GRACE, and its successor, GRACE Follow-On, map the continent using an entirely different physical principle: gravity. The GRACE mission consists of two identical satellites flying in tandem, precisely 137 miles apart. As the lead satellite passes over a region with a slightly higher mass concentration, such as an underground iron deposit, a massive mountain, or our mysterious circular anomaly, the localized gravitational pull increases, subtly tugging the lead satellite forward and widening the gap between the two spacecraft. Conversely, when passing over a less dense area, the gap narrows. By using an ultra-precise microwave ranging system to measure variations in the distance between the two satellites, down to a fraction of the width of a human hair, NASA maps the Earth's gravitational field in real time. When you overlay this orbital gravity mapping with the laser altimetry of ICE-SAT-2, which uses a green laser split into 6 distinct beams to measure the shifting height of the ice surface with millimeter accuracy, the invisible world becomes undeniably clear. Scientists can see where the ice surface is sinking because a hidden subglacial lake drained miles below, or where the ice is bulging upward because a geothermal plume is generating immense water pressure at the bedrock interface. This technological alchemy does more than just generate stunning color-coded maps. It strips away the isolation of Antarctica, revealing a landscape that is shockingly alive, constantly shifting, and surprisingly fluid. What kind of geography emerges when you finally strip away the ice? What actually lies at bedrock? When you finally peel back the multi-mile shroud of frozen water using NASA's radar, sounding, and satellite gravimetry, the landscape that emerges is not a flat, featureless plain. It is a hyperdynamic, rugged, and brutal continent that boasts some of the most extreme topography on Earth. If you could magically evaporate the Antarctic ice sheet tomorrow, you would witness a sprawling network of jagged mountain ranges, profound tectonic rifts, massive river systems, and enormous subterranean lakes trapped under immense hydrostatic pressure. This is a hidden empire of rock and water that has been sealed off from the rest of Earth's atmosphere for up to 34 million years, preserved in total darkness and crushing isolation. The most mind-bending geographical feature mapped by scientists is the Gamburtsev mountain range. Located in the heart of East Antarctica, these peaks are roughly the size of the European Alps, stretching for over 750 miles with jagged summits that soar to nearly 10,000 feet. Yet, they are completely invisible from the surface, buried beneath a solid layer of ice that is over 2 miles thick. What makes the Gamburtsevs a profound geological paradox is their sheer crispness. Normally, an ancient mountain range subjected to millions of years of continental rifting and glacial movement would be ground down into smooth, rolling hills. Instead, NASA's ice-penetrating radar revealed sharp, steep ridgelines and deep alpine valleys that look as though they were carved yesterday. Because the ice sheet froze over them rapidly millions of years ago, it effectively encapsulated them, protecting them from atmospheric erosion and locking a pristine, prehistoric alpine landscape in a deep freeze time capsule. But the topography drops from majestic peaks into terrifying depth. On the opposite side of the continent, beneath the Denman Glacier in East Antarctica, international teams mapped the absolute deepest point on continental Earth, the Denman Canyon. Plunging more than 11,500 feet below sea level, this colossal trough is far deeper than the Grand Canyon. It is a stark reminder of the sheer tectonic violence that shaped the Antarctic plate before it drifted into its current polar position. If the ice filling this trench were to melt, the ocean would rush in, creating a massive, deep-water fjord that would slice deep into the heart of the continent. Understanding the exact geometry of these deep trenches is critical. They act as subterranean highways that can allow warming ocean water to penetrate deep inland, bypassing the outer defenses of the coastal ice shelves. Beyond the dry rock, the most startling revelation of modern subglacial geography is that Antarctica is incredibly wet. The continent is crisscrossed by a vast interconnected network of subglacial rivers and over 400 liquid lakes. The largest and most famous of these is Lake Vostok, a body of water roughly the size of Lake Ontario, buried under nearly 2.5 miles of ice. For decades, scientists assumed that the bottom of the ice sheet was frozen solid to the bedrock. However, the immense weight of the overlying ice sheet creates an environment of extreme hydrostatic pressure. This pressure, combined with the natural insulation provided by miles of ice and a steady trickle of geothermal heat from the Earth's crust, lowers the melting point of water, allowing vast reservoirs to remain liquid even at temperatures well below freezing. These lakes are not stagnant, isolated puddles. They are part of a dynamic, pulsing hydrological system. NASA's ICSat satellites have tracked dramatic, real-time changes in the surface of the ice sheet, showing sections of the ice buckling upward or sinking by dozens of feet within a matter of months. This happens because high-pressure subglacial rivers are actively draining water from one subglacial lake and dumping it into another miles away. The water acts as a high-pressure hydraulic fluid, lifting the multi-mile ice sheet off the bedrock and letting it float ever so slightly. When this water eventually drains out to the continental margins, it acts as a slick lubricant, fundamentally shifting how fast the glaciers move. This complex labyrinth of hidden water and jagged rock forms the foundation for a dark, pressurized world, one that scientists are discovering is far from dead. If liquid water can survive under miles of ice in total darkness, could life find a way to do the same? The biology of absolute isolation. When the first deep core drills finally broke through the bottom of the Antarctic ice sheet and breached the pristine waters of subglacial lakes like Lake Mercer and Lake Vostok, scientists braced themselves for an eerie reality. They were opening a biological vault that had been sealed shut for millions of years. In this deep subterranean ecosystem, there is no sunlight. The temperature hovers near freezing, and the water is subjected to crushing pressures hundreds of times greater than the Earth's atmosphere. According to the foundational rules of biology taught in every standard textbook, this should be a wasteland, a place completely devoid of life. Instead, what NASA-backed research teams and international microbiologists found under the ice was a thriving, bizarre safari of microscopic organisms that have rewritten our entire understanding of how life survives in the universe. The life forms inhabiting this subglacial labyrinth are essentially evolutionary ghosts, completely cut off from the surface world since the continent froze over during the Oligocene epoch. Because there is no sunlight to trigger photosynthesis, the entire food chain has to reinvent itself from scratch. Instead of relying on solar energy, the microbes down here utilize a process known as chemosynthesis. They are literally rock eaters, or chemolith autotrophs. These specialized bacteria harvest energy by breaking down the mineral bonds of the ancient bedrock beneath them. They feast on iron, sulfur, and manganese deposits that are ground into a fine dust by the immense, grinding weight of the moving ice sheet above. By metabolizing these raw chemical compounds, the bacteria produce organic carbon, creating a baseline energy source that supports an entire hidden web of microscopic predators. When scientists analyzed the water samples recovered by clean drilling rigs, which use sterile, high-pressure hot water to melt through the final layers of ice without contaminating the pristine lakes, they discovered thousands of distinct species of bacteria and archaea. The sheer genetic diversity was staggering. Some of these microbes are unique to the subglacial world, possessing highly specialized enzymes that allow their cellular structures to remain flexible and functional under immense hydrostatic pressure. Others are closely related to ancient ocean-dwelling bacteria, suggesting that they are the direct descendants of marine life that inhabited the region back when Antarctica was a warm, open sea. These organisms have spent millions of years evolving in a parallel evolutionary track, totally unaffected by the extinction events, climate shifts, and biological revolutions that shaped the surface of the planet. But the discoveries didn't stop at single-celled bacteria. In the dark, brackish estuaries, where the subglacial rivers finally empty out into the dark waters beneath coastal ice shelves, researchers dropped specialized robotic cameras down through narrow boreholes. What flashed on the monitor screens shocked the scientific community. Darting through the freezing, pitch-black water miles away from the open ocean were complex, multicellular animals, tiny, transparent amphipods, crustaceans that resemble small, ghostly shrimp, were filmed swimming alongside translucent jellyfish and small fish. These animals are operating in an environment with zero light, surviving on whatever organic debris washes out from the subglacial lake networks or down from the underside of the ice shelf. The existence of complex animals in these deep freeze sanctuaries proved that life does not just tolerate extreme conditions, it adapts, colonizes, and claims them. The discovery of this hidden biosphere has profoundly shaken up the scientific community because it shatters our traditional Earth-centric definitions of habitability. For centuries, humanity assumed that life required a warm sun, a breathable atmosphere, and a stable climate to thrive. Antarctica's subglacial lakes have proven that as long as you have liquid water, a steady source of mineral energy, and a bit of geothermal warmth, life will find a way to carve out a foothold. These microbes are the ultimate survivalists, thriving in a world of absolute isolation where the day-to-day conditions haven't changed in 10 million years. But as scientists look closer at how this hidden water network interacts with the rest of the planet, they are realizing that this pristine isolation is starting to fracture. What happens when the external world begins to force its way into this ancient, delicate system? The real-time crisis. The stunning revelation that Antarctica conceals an active subterranean biosphere and a jagged, Alps-sized mountain range is enough to captivate any imagination. But for the teams of scientists tracking NASA's orbital feeds, the true urgency of modern polar research is centered on a much more immediate and disruptive physical reality. The real crisis unfolding across the frozen continent is not a hidden geological secret or a prehistoric anomaly. It is a rapid, visible transformation of the coastline that has the potential to fundamentally reshape the map of human civilization. Utilizing nearly 3 billion unique data points collected by space-borne instruments over consecutive decades, researchers have watched the protective outer defenses of the continent begin to structurally fail. Let's have a look at the unique mechanical engineering of the Antarctic coastline. The massive ice sheet that blankets the continent does not simply sit static on the bedrock. It is under the constant, crushing influence of gravity. This immense pressure forces the interior ice to flow outward toward the sea, moving down glacial valleys like a slow-motion conveyor belt of solid water. When these glaciers finally reach the edge of the continent, they push out over the open ocean, forming vast, floating platforms of solid ice, known as ice shelves. These shelves, some of which are hundreds of meters thick and span areas larger than entire states, serve a vital, protective function for the interior of the continent. They act as massive architectural buttresses, effectively plugging the mouths of the glacial valleys and slowing down the flow of the land-based ice behind them. The structural integrity of this entire system depends on a precise anchor point known as the grounding line. This is the exact boundary where the massive terrestrial glacier leaves the solid bedrock of the continent and begins to float on the ocean water. As long as the ice shelf remains thick, heavy, and firmly wedged against the surrounding coastal bays, it exerts a powerful back pressure that locks the glacier in place, keeping the interior ice sheet stable. However, NASA's Jet Propulsion Laboratory has demonstrated that this delicate structural equilibrium is breaking down at an accelerating rate. The primary catalyst for this shift is not the warming air above the ice sheet, but a hidden, highly destructive process occurring completely out of sight on the underside of the floating shelves. Satellites like Cryosat-2 and the ICSat missions have revealed that warm, dense marine currents are actively breaching the continental shelf, flowing deep underneath the floating ice platforms. This relatively warm saltwater circulates through the subglacial cavities, melting the ice shelves from the bottom up in a process known as basal melting. The structural damage is not uniform. Instead, the shape of the ice shelf's underbelly actively traps the ocean heat. The warm water carves massive inverted river valleys and deep structural channels directly into the underside of the ice, causing the shelves to thin unevenly and lose their structural rigidity. A groundbreaking synthesis of satellite imagery revealed that since 1997, the outer edges of the Antarctic ice sheet have shed a staggering 12 trillion metric tons of ice due to this relentless bottom-up erosion and subsequent calving. When an ice shelf thins and weakens beyond a critical structural threshold, the consequences for the interior glaciers are immediate and dramatic. Without the physical resistance of the floating buttress, the grounding line begins to retreat backward into the deeper basins of the continent. This process lifts the terrestrial glacier off its stable bedrock footing, effectively removing the architectural plug from the bottle. Once this anchor point is lost, the inland glaciers experience a sudden acceleration, rushing toward the ocean up to 8 times faster than their historical baseline speeds. This turns a localized coastal melting event into a massive continental drainage system, directly transferring land-based ice into the global ocean. The most critical focal point of this structural instability is the West Antarctic Ice Sheet, specifically the massive Thwaites Glacier. Often referred to by the media as the Doomsday Glacier, Thwaites is a colossal block of ice roughly the size of Florida. What makes Thwaites uniquely dangerous is its underlying topography. The bedrock beneath the glacier tilts downward as it moves inland, creating a deep, subterranean basin that sits far below sea level. As warm ocean water erodes the grounding line, it pushes into an increasingly deep trough, allowing the ocean to penetrate further and further inland under the weight of the glacier. If the Thwaites ice shelf collapses entirely, it will trigger a runaway chain reaction, unleashing a colossal volume of ice that holds enough mass to raise global sea levels by more than 2 feet on its own, while destabilizing neighboring ice sectors across the entire western half of the continent. The massive influx of cold, fresh meltwater pouring off the thinning ice shelves threatens to disrupt the delicate balance of the Southern Ocean. Because fresh water is less dense than salty ocean water, it forms a buoyant layer on the surface that can alter deep-sea ocean currents, potentially slowing down the global conveyor belt that distributes heat and nutrients across the entire planet. At the same time, the accelerating loss of terrestrial ice means that global sea levels are rising at a pace that forces coastal cities around the world to confront an entirely new era of flooding and erosion. The real alarm echoing through NASA's research centers is driven by the realization that these massive polar buttresses are deteriorating faster than any historical model anticipated, turning a remote landscape of rock and ice into the primary engine of global geographic change. How do the lessons learned from this melting world apply to the frontier of space? From the South Pole to the moons of Jupiter. The intensive effort to map Antarctica's subglacial geography, analyze its extreme microbial ecosystems, and monitor its structural stability does more than just answer critical questions about our own planet. For NASA, this frozen continent is also the ultimate cosmic laboratory. The extreme conditions locked beneath the Antarctic ice sheet provide a direct physical proxy for some of the most intriguing and hostile environments in our solar system. By developing the technology needed to peer through miles of solid ice on Earth, scientists are actively building the blueprint for humanity's next great frontier, the search for alien life on distant, frozen worlds. The primary targets for this interplanetary reconnaissance are the icy moons of the outer solar system, specifically Jupiter's moon Europa and Saturn's moon Enceladus. For decades, planetary scientists viewed these distant bodies as inert, frozen spheres of rock and ice. However, data from deep space probes like Galileo, Cassini, and the ongoing Europa Clipper mission have revealed a reality that closely echoes the subglacial landscape of Antarctica. Europa is enveloped in a global crust of solid ice that is estimated to be 10 to 15 miles thick. Yet, beneath that staggering frozen shield lies a vast global ocean containing more liquid water than all of Earth's oceans combined. This deep ocean environment is kept liquid by gravitational tidal flexing, which stretches and compresses the Moon's interior, generating immense geothermal heat at the seafloor. The discovery of chemotrophic bacteria thriving in the pitch-black waters of Lake Vostok and Lake Mercer proves that life does not need sunlight, a traditional atmosphere, or an external ecosystem to establish a permanent foothold. If extreme microbes can build an entire food chain under the crushing weight of the Antarctic ice sheet by eating raw minerals from the bedrock, there is no scientific reason why similar life forms cannot thrive on the rocky floors of Europa's subsurface oceans. Antarctica provides the empirical proof that a dark, high-pressure water system is a perfectly viable habitat. To explore these alien oceans, NASA is using the Antarctic Plateau to field-test autonomous drilling systems, deep-diving subglacial rovers, and miniature clean sampling probes. The exact same laser altimetry, satellite gravimetry, and ice-penetrating radar technologies developed to map the Denman Canyon and track the grounding lines of the West Antarctic Ice Sheet are currently being adapted for orbital missions around these distant moons. When a future robotic probe eventually lands on the cracked, icy surface of Europa to deploy a thermal drill into the abyss below, its operational framework will be rooted in the pioneering work conducted in the most isolated corners of the South Pole. By unlocking the secrets of the world hidden beneath our own ice, we are taking our first concrete step toward discovering whether life is a unique earthly miracle or a phenomenon that thrives across the frozen dark of the cosmos. If this fascinated you, consider subscribing to the channel and check all of our videos out here. Thanks for watching.